Welcome to Breadboarding. In the previous video we covered an introduction to programmable logic devices, and we covered the ATF16V8 chip, which is probably the easier of the two chips here to work with. In this video what we're going to be doing is looking at more of the background information on WinCUPL and the CUPL programming language which is used for these, and then we're also going to have a bit of a dive into the ATF16V8 and look at some of the complications of using this particular chip. So this is the second part of the Programmable Logic Devices mini-series for Breadboarding Labs. And first of all, what I'm going to do is to have a look at running WinCUPL on Windows XP. Now I'm running VMware Workstation here. I believe you can now get VMware Workstation for free for private use. And what I've done here is I've installed Service Pack 3 and we've now got WinCUPL here. You can see we've got the examples and things installed here. Now it's interesting that if you go into WinCUPL here, where we were having problems with it crashing quite frequently, then in fact if we open one of the sample files, so I've just been using adder.pld here, and you'll see here that on the right hand side the project view is actually showing the PLD file and the simulator file on the right hand side here, which is different from what we saw in the current version running on Windows 11. And if we now just go in and check that we've got the compiler options for the fused plot equations and everything else, yeah, that's correct. And if we now just run this, you'll see the compilation successful, and in fact all the output files are now shown here. So this is the way how WinCUPL is supposed to work, although on later versions of Windows it doesn't do this. Now what I've tried to do is use some of the monitoring tools that I've used in the past for tracing problems with Windows applications. So Process Monitor, for example, from sysinternals will allow you to check all of the registry settings and all the file system reads and writes. And I've gone through there to try and see what the difference is between this and the application running under Windows 10. And I haven't actually been able to get to the bottom of what actually causes the problem. What I do know is that when we run in Windows XP, everything works okay. And we can also check to see all of the help documentation here as well. So if we go into the help here, we can see that we've got all of the classic Windows help documentation here. If we try and do the same thing on later versions of Windows, we just get an unhelpful page from Microsoft to say that these old help-based features are no longer supported. So when we look at the documentation, I'm going to look at how to get access to some of these help files so that we can actually get some of that information for use on current versions of Windows. And we can also see that this project view does actually make things a bit easier. So for example, we wanted to have a look at the output files here, we could do so. So it certainly made sense the way how it was working. I've not been able to get to the bottom of what was causing this problem. You do need to change the permissions on WinCUPL running under Windows XP to give update access. So you do that and apply it. Otherwise it doesn't actually save the changes you make to the configuration. But other than that, there were no other changes I needed to make. I've done the similar changes to later versions of Windows, tried running in compatibility mode and also with administrator privileges, and it makes no difference. So for the moment, I'm content with the fact that this project view, although it's nice to have, it's not actually that important. And as long as we actually turn the project view off, then in fact it will function quite adequately. So we've seen that WinCUPL runs okay on Windows XP as would be expected, and we've also seen that there is a certain amount of documentation in Windows help format. So what I'm going to do now is to have a look at the various sources of documentation for WinCUPL and the CUPL language itself. So a lot of the documentation is actually provided under the WinCUPL atmel help folder. So these documents here, which I'll be going through, are also accessible through the help menu. So although the Windows help doesn't work here, we can access these from here. Now, what I would suggest we do first of all, I'm going to go through the contents of these. Not all of the documents are that helpful, but there are a few key things. So as we go through the release notes and the dev help in particular, I'll just call out certain things. So the release notes for the latest version, which is version 5.30.3. This appears to be from around 2003. You can see that system requirements are Pentium-based PC, 32 megabytes of memory, and Windows 98, NT4, 2000 or Windows XP. So this was the last release of this. And this release notice is quite useful because it actually includes some information about the later series of devices, in particular the 16V8C and the 22V10C, which are the devices that we like to be using. Tend to be using the V8B, in fact, I think. Pin 4 information in there. And in addition to that, there's some information about the ATF16V8, which we're not going to worry about. It's a bit too complicated. But this table here is actually quite useful in that it shows all of the supported Atmel Programmable Logic Devices. So we can see down here that we've got the ATF16V8B, which is the chip that you can still buy from Mouser, and you can see the various device mnemonics here. And I'll be going into this in a minute when we look at dev help. But what it does recommend is that we use by default the G16V8A, and this is a generic default device that will actually choose these other ones as appropriate. Then we've also got down here the ATF22V10C, which is again the other chip, and this is much simpler. We just have to worry about the G22V10. So this just summarises. Windows XP is the last version, includes information about the power down mode, particularly pin 4. If you do use a power down, then you need to make sure pin 4 is handled appropriately. And it provides all the information about the Atmel Programmable Logic Devices, in particular the 16V8B, that this is the one that causes the most confusion, and until you find this information it can be really quite challenging to work out how to use these devices. And then we can also see then that we've got the 22V10 with the G22V10, and if we want to use the power down mode, then we have the CP on the end here. So that this information, trying to find this information isn't entirely trivial. So finding it between the release notes and then the dev help is actually where some of the other information is. So we'll have a look at the dev help now, and these are the two main documents that probably help you to get programming these things working properly. So dev help looks like it's just a text document that's been converted to PDF. And you'll see here, I think the format of this is probably in the form of where you choose devices. It looks like it's perhaps some of the information that you can see in this, although it doesn't include all of the information. So you'll see that if you look at the different devices in here, it'll actually show you some information about the different parts, how many pins there are, what the different pin definitions are here, but it doesn't include all the information that I'm going to be showing you here. So this one here, if you remember on the previous slide, CP means that this is a pin controlled power down. Now again, for the projects that I'm doing on 5 volts retro computing, we don't really need to worry about that, so I'm going to skip over that for now. A lot of the information in this bit here is very similar to the next device. Then we've got the G16V8. Now this is the old default, but is not the recommended one that the release notice recommends us to use, the G16V8A. So I'm not going to look at that one. So now we've got the G16V8A. So we're going to go through this in a little more detail. So it shows us we've got a pin count of 20. There's a total product terms of 64. We don't have the pin control power down. But the extensions here is important, and when we come to look at some of the documentation, you'll see that there's many extensions in the documentation on CUPL, but in fact this particular 16V8 chip only uses 2 of them. So the D means register and OE is output enable. Now it also just shows here that this is the ATF16V8B, however the release notice also showed all the other chips that were also compatible. So you kind of need to combine information from multiple documents to actually make sense of which chips should be using which configuration. Now this says this device emulates 3 different PAL architectures, and we've got multiple modes. And the problem here is that our registered mode here is actually sneaking. It's very easy to miss this. So the first mode is the most complex, the registered mode, where we've got flip-flops. You can see here the mnemonic for that is G16V8MS. Now if we use that, then this is automatically chosen. So if you've chosen the generic one here, the G16V8A, which has the asterisk there to say this was the recommended one, then it will in fact actually switch between these various mode mnemonics automatically. So the compiler will automatically choose which one based on what you've got. Now what you'll notice here is we've got this section for input only, and input output. And you'll notice that the pins that can do this are different depending on the mode, and that in registered mode that pin 1 is always the common clock and pin 11 is the common output enable. However, the output enable is automatically applied to registered terms but not to the combinatorial ones, and I'll show what that means when we look at the datasheet. Now complex mode, you'll see this mode is automatically chosen when the PLD source has output enable terms but doesn't use any registers. So if you don't use flip-flops but we use output enable, then it will choose this mode. And you will see here that in fact the pin 11 can now actually be used as an input, although you may very well choose to use it as output enable, but you don't have to. And you'll see that the output only terms are 12 and 19, and they're no longer input output as they were previously. And then we look at the simple mode. So this means we don't use any output enables, and you'll see again that the input only and the output only are different. So again, you can see here that the pin numbers here are actually different, and this can cause quite a bit of confusion when you're trying to do some of these designs, which is one of the reasons why I was kind of saying that if you use it in simple mode, then it's fairly straightforward, but these other ones can get a bit tricky to get it all right. So if we actually use the G16V8A, then it will actually choose between these modes automatically. However, that can actually just make things more complicated, because then something stops working that was working because you've added something to the design and you now find it switched from one type to the other, and some of these output only, input only type things also change. So that's what I'm going to cover a little bit later when we talk about this particular chip in more detail. The other bit in here that we need to worry about really for the moment is the G22V10. Now again, in this particular one we want to ignore this one because this is pin controlled power down. Pin 4, if we didn't set this to 0, when you set it to 1, then in fact it would power down the chip. So if you weren't aware of that, it would certainly cause confusion when you were testing it. So this is one we're going to be using on all the examples, and what I've been using on the breadboard PC. You can see here that the G22V10 has 132 product terms, no power down, but you'll see here the extensions are in fact output enable and D, similar to the 16V8, but we've also got asynchronous reset and synchronous preset are also additional terms that can be used. And when we look at the documentation, this is why this becomes important. And you'll see, although the device names here is only the ATF16V8B, when we looked at the list here, we'll also see that the 10C and CZ are also supported in this form as well. So the information on here is quite challenging to get your head around when you're first learning this, and it's taken me a while to fully get my head around it. The other thing here is that I did start using the P22V10 at one point in time. However, this is for the AT22V. This is a slightly older technology that used EEPROM rather than Flash. So again, don't get the P22 and the G22 confused, as it might cause problems. So these two files here, release notes and dev help, are really quite important for making sure you get the right mnemonics for the device to actually do your programming. If you don't get those right, then you can be wasting an awful lot of time. Now, some of the other documents in the help I'm not going to go through in detail. The bug and the fix documents mainly relate to the ATV750, the 2500 and the F1500, which are the more complex chips. Again, this is all from around February 2003 when the last update to this was. Fitter PDF is to do with the ATF1500. Again, that's only available in the PLCC 44 output, so we're not really going to worry about that too much. There is a very basic tutorial on WinCUPL and WinSim, but it's not really particularly useful. But there is the list of the examples. However, out of the 41 samples that are provided, only 7 are really appropriate for the 16V8 and the 22V10. So the vast majority are for these more complicated chips. And the problem with that is because of all of the extra extensions, then this can really be confusing, because the only extension you need to worry about I've got summarized on a couple of slides' time. Now, the CUPL User's Guide, there's various versions of these that I've come across, and I'll take you through some of these, but you'll see that the 1998 Logical Devices version, so Logical Devices were the original developers of WinCUPL before it was sold to Atmel, before Atmel were then acquired by Microchip. There is then a 2012 version, which I think has come from University of Southern California, which is again a bit shorter, but does have some samples explained in some detail. And then there's the Atmel CUPL User Guide, which is only about 43 pages. But there is actually quite a useful tutorial from about page 35. Now, I should say that a lot of the information from this earlier document seems to have been included in the WinCUPL help files, which we'll come to in a minute. So let's have a look at these user guides just to see what sort of information is there. So this is the earliest user guide. This is from around, I think, 1998. And this is the original Logical Devices one. And you'll see this one is actually really quite long and has a lot of detailed information about all the individual terms and things within the CUPL language, and also the simulator as well. I'm not really going to look at the simulator that much, but you can see there's about 150 odd pages of documentation just referring to the CUPL language. And there is a design example that goes through, and it talks about the sample PLD files. Unfortunately, these sample PLD files, there's quite a number in here, but most of these haven't made it into the later versions of WinCUPL. Then this version is, I think, a version that was created around 2012 by the University of Southern California. Again, this is quite useful. There is actually around, I think, a page 121 or something. So this talks about sample PLD files. Again, not all of these samples are actually included in any of the releases I've seen, but there are actually walking through the simple gates. So the gates is what I showed in the earlier video. So it's a very simple sort of defining inverters, ands, nands, ors, nors. So it goes through and explains all of that, and then goes on to explain how to convert TTL design. And this is an example of using chip selects and simple logic equations. Then a 2-bit counter, which introduces some of the concepts between doing counters using the registers in PLDs. Then there's a decade up-down counter, so count 10 PLD I think is included in the WinCUPL examples. It has a fair old bit about that. Then a 7-segment display decoder, which again I don't believe this is in any of the other samples. So this is one that is quite interesting and may very well use in some tutorials I'm looking at doing. Counter with load and reset. So these examples don't appear in some of the other documents, so they're quite actually useful to have these things explained. There aren't many explanations elsewhere. Then finally we've got the Atmel document. Now this is quite a bit shorter and doesn't have quite as much information in it, and I think this information was also split between the user guide here and also the online help. But there is a tutorial for gates in here, so again the tutorial for the count 10. So there's some of this tutorial information which is quite useful, but it is pretty short, this particular one. So I would suggest that probably this original Logical Devices one is probably the one to have a read through first. Some of the information might be out of date, but it doesn't look like it's actually changed very much. So this just really summarises what we've got here. Now, there are a load of microchip documents on the ATF16V8C. I've actually downloaded a lot of these. I'll put them up onto GitHub for the breadboarding labs under a new PLD project. Now, the WinCUPL help files, you saw that when I was running Windows XP, we could actually see the help files. So we can't view old Windows help files in modern versions of Windows, but there is a website here that will actually allow us to view them and to actually extract the data from them. Once it's loaded up, we do have to enable adverts and things for this to actually work. What we can do is to choose a file. So if I just choose the WinCUPL help file there. Now, I have run this previously when I had the ads and things enabled, and basically what this produces is allows you to create a zip file. So the zip files that have been created here basically produce this sort of web page with all of the information in it, and you can then save this as a rich text file format. And what I've done, certainly on the reference information here, is I converted it into rich text, and then I had to go through the document and actually include a lot of, for some reason, the images and things weren't included actually automatically by converting them. But this actually includes all of that information, and you can see that it's got all of the tables and all of the images and things in there, a lot of the diagrams. And this really includes virtually all the most detailed information I've seen yet. And you'll see here that as part of this, these are all the extensions that are available. So if you think of, there's probably a best part of 30 odd extensions there that can confuse things, certainly when you're looking at the examples. And in fact, the only ones that are used in the ATF16V8 is the D and the output enable. And what I've done in this list here, what I've actually done is gone through all these extensions and actually worked out which ones are used in which chips. So these are all the extensions we've got here. So I think there's about 42, I think, in total. And in fact, if we look at the 16V8, it just uses D and output enable. If we look at the 22V10, this just adds asynchronous reset and synchronous preset. And then you can see the other two here, the 750C, which I do have on order, should be arriving later on this week. So I'll hopefully be able to do an update video to see if I can get the ATV750C working. You'll see this has quite a few more, and in particular this actually allows the clock to be specified on each flip-flop, which is one of the biggest limitations of the current ones that we're actually using. So hopefully I'll be able to do an update video in the next week or so once I've got these chips. So these are the extensions. When we're actually looking at the documentation, we only need to worry about the .d, .output enable, and the asynchronous reset and the synchronous preset are also used in a number of the examples for the ATF22V10. So I'll include the CUPL reference in PDF and Word docx format. I'll put that on the GitHub as well. So based on the dev help and the datasheet, the ATF16V8 has 3 modes which you need to be aware of. So simple basically has no output enable terms and no registers. Complex has output enable and you can configure it at a pin level. And in registered modes, this is using flip-flops. Then pin 11 is defined as output enable for all registers, whereas all the combinational logic can have output enable specified by pin. So there's also quite a few variations, as we saw when we were looking at the dev help PDF, variations in which pins can be used for input only, output only, and input and output. So what I'm going to do is have a look at the datasheet for it, and then there's an example here that I produced earlier on in the project where I'd run out of 74LS574 ICs, and I actually did one using this 16V8, and it was almost identical to the layout of the original 574. I think 2 of the signals were reversed. So we're going to look at the ATF16V8 datasheet and also the GAL16V8. The reason why we need the GAL one is because this will include the fuse numbers and things on it, which the ATF one doesn't have. So when looking at this, we can see that pin 11 is output enable when in registered mode, and in other modes, then the simple mode, then we don't have any output enable at all, and in the complex mode we can use output enable on this pin, or we can use any other pin or any other term to define output enable. So there's a little more information in this ATMEL device than we had compared to the 22V10, certainly when we compare it with the data sheet for the GAL here. You can see the equivalent information about registered, complex and simple, and there are some nice diagrams in here. The main thing that the GAL includes is various of these configuration options, such as the SYN AC0 and AC1, which determine which mode each of these macro cells is running in, whereas the ATF version doesn't actually include that information. So you see in the registered combination, we have the register with the output. Whether we're using positive or negative output is determined by the XOR term. There is a common clock which is used for all of the registers, and the output enable is also defined common for all register configurations. Where we've got pins in registered mode which are not using the D flip-flop, then in fact the output enable can be determined by any general term. So you might generally just map this to output enable, but if you wanted to, you could have another combination of logic that determines output enable for this particular one, and you can see that we can actually feed the input value on that pin back into the matrix, whereas in the registered mode, similar to when we looked at the 22V10, the feedback is actually coming from the Q bar output of the register, and therefore you cannot take an input from the pin here in registered mode when we've got a register configuration. But there's no mention here of either of the fuses which are used to determine which of these modes we're in and which mode the pin is in, whether it's in the registered mode or the combinatorial mode. If we compare it with the GAL, we can see here that there are two global bits. SYN and AC0 control the mode configuration for all macro cells. The XOR bit of each macro cell controls the polarity of the output of any of the three modes, while the AC1 bit of each macro cell controls the input-output configuration. So basically this AC0, AC1, XOR and SYN control the configuration of the macro cells, and the lattice GAL configuration for the same things we saw on the ATMEL sheet. This is the same diagrams, the registered configuration in registered mode and the combinatorial configuration for registered mode, but this also includes SYN equals 0, AC 0 equals 1, SYN equals 0, AC 0 equals 1, and you can see the difference between the configuration is AC 1 equals 0 and AC 1 equals 1. Here's the way how it switches between these two modes. Then when we go to the registered mode logic diagram, we can see that clock goes into all the clocks on the output logic there, and output enable is actually feeding into all of these. Where we're not using the register, then in fact the output enable can actually come in through one of these terms here. So it just depends on whether or not we're using the register or not. Then in complex mode, this basically means that we need to have the output enable configured, but we're not using any registers. When we look at the GAL datasheet, we can see here that the GAL datasheet shows us what the fuse numbers are for the XOR, for the AC1. You can see all the fuse numbers here, and also the fuse number for SYN and for AC0. So we've got all the fuse numbers here for doing the configuration, which the ATMEL version doesn't give us. Then in complex mode, this shows us that in fact in the combinatorial version we have actually got two configurations. So you'll see pin 13 to 18 have got the feedback going back into the AND array, and you can see as well we've got the SYN equals 1, AC0 equals 1, AC1 equals 1, but also that pin 12 and pin 19 are configured in a way that there's no feedback. So this is some of the information that we saw in the dev help that indicated which pins were able to do feedback and input output only, all that sort of stuff. So then when we get to simple mode, there is mention of this S1 fuse here, which is used to disable the output or not. If the output is disabled, then this becomes an input. And again, we can see here that pin 15 and 16 do not have this feedback path. And rather confusingly, the way how this diagram shows the complex mode. So we can see in complex mode that pin 19 doesn't have a feedback directly like these ones do, because this is actually used for the pin 1 feedback. And if you look down here, pin 11 uses this feedback, but there's no feedback path for this one either. But you kind of have to work that out. It's not really quite as clear. And then finally, for the simple mode, we can see that in fact that the feedback for pin 19 is actually coming back through this one, feedback from 18 is coming back through this one, and in fact that 15 and 16 do not actually have their own feedback. So you see there's no feedback coming from here and here, and then there is feedback from pin 12. So these PLDs, although they're on the face of it simpler, the actual variations in the different modes does make things a bit more complicated to get things working, which is one of the reasons why I would say that generally if you've got simple mode where you're just doing some basic address decoding or something, then this is probably absolutely fine. But if you're starting to do more complex things, it's probably going to be easier to work with the 22V10 rather than these ones. Now if we go to the original GAL datasheet again, we can then see for the complex mode that this is again identifying that the feedback exists for all pins apart from 19 and 12. And again, we've got all the fuse numbers on there. And then for simple mode, again, we've got the various values here for AC0 and AC1 for the simple mode. And this identifies for all the configurations apart from 15 and 16, and this then is 15 and 16 don't have the feedback. And then if the pin is dedicated to input, then in fact, then this is the configuration here. So when we were looking at the dev help, so this was the G16V8A, which is the one recommended. You can see that for registered mode, we had these pins here. In complex mode, there's the pin functions here. And then in simple mode, the pin functions here. So we need to take that into account when designing things. Now, one of the more complicated examples I managed to put together using registered mode was the version of the 74LS574 sort of octal latch. So the only real difference between this PLD and the 74LS version. So this is the chip layout of the ALS and ALS 574. So you can see we have outputs Q1 to 8 or 0 to 7, inputs D1 to 8 or 0 to 7. The clock, which latches the values, is on pin 11, and the output enable is on pin 1. However, when we look at the pins that we have available on our PLD, the output enable and the clock are actually swapped around. So the rest of it is pretty much the same. It doesn't really matter whether it's 0 to 7 or 7 to 0. And you will see here that pin 1 is just identified as a clock. If we didn't identify pin 1 as a clock, it will get used as the clock anyway. We have D0 to 7 going from pin 9 to pin 2. Now, pin 11 is defined as output enable, but we're not actually using output enable in any of the terms here. So we could have put an exclamation mark here, probably would have been better, but it doesn't really matter too much. And then what we're saying is the outputs for this range here. And basically what this does here is says all of the D input flip-flop for all of the Q0 to Q7 are set to the corresponding D0 value. So that value gets latched when clock is on the rise, and this basically produces us a 574. Now I would have to say that to work out to get all of these things to actually work and getting all this syntax right, it did take me a little while. And the other key thing really is making sure that we have the correct, it's a 16 not 17, that we have the correct device. So in fact, having this as a G16V8MS, if we check back to our documentation, we can see that G16V8MS is the registered mode. And if we have a look at the doc file for that, we can see that all the Q values, the D inputs are set to D0 to D7. And we can also see that clock is on pin 1. We're not actually, the output enable here will automatically be assigned on registered mode, then the output enable is automatically assigned to all of these pins, and it is actually the inverted output enable which is actually used to do this. So I'm just going to compile the 574 PLD. So it's already loaded here, we're just going to run that. So that's compilation successful. Then in XG Pro, we're just going to program it. So it's currently set to the 22V10 that we used last time. So we're just going to switch it back to the ATF16V8B. And if we just read it to make sure that everything's okay. Yep, that's all read okay. It's a blank chip, everything's ones. Now if we just load the 74LS574 JED, and we program that. Okay, so that said it was successful. And I think I still have a test for this here. So if we go down here and look, we can see we've got the GAL16V8 74LS574. So you can see it's just a couple of tests here. We test that, yep, so that's all passed. So in this video, we've gone through looking at the documentation and showing that WinCUPL could run quite successfully on Windows XP, looking at the Windows help, looking at all the documentation. We've gone through in a fair bit of detail the ATF16V8B, which is a bit more complicated to configure just because of the different modes it has. And we've shown able to program it, and we've programmed it in the registered mode as well. So in the next video, what I'm going to do is to dig into the examples in a bit more detail and go through some of the different configurations that are in the samples and explain how that all works. If you're not interested in that, then the video after that, I'll be going through showing how the PLDs actually work. So going into programming all the fuses and things like that. I should also then be looking at the ATF750C. So this is the revised version of the 22V10, which is a lot more clever things it can do. So if you don't want to miss out on the future videos, please hit subscribe. And if you found the content useful, please hit like. Thanks for watching.